Previously, we've talked about alkenes on their own. So when you have one double bond in a compound and what reactivity that imparts on a system. Now we're going to talk about having systems that have at least two double bonds. Now when you have two double bonds and they're separated by at least two single bonds, you have what's called an isolated diene. So here we have our sp2 carbons separated by an sp3 carbon. And that sp3 carbon prevents these sp2 carbons from delocalizing their electrons. With what's called a conjugated system, you have at least three sp2 carbons in a row in order to delocalize all of those pi electrons, and it creates a very stable system. Conjugated dienes can be viewed on UV-Vis spectroscopy. We didn't talk too much about UV-Vis spectroscopy in our analytical module, but the UV-Vis spectroscopy is where we see these conjugated systems because they have a tendency to either be visible or absorb in the visible or the UV range. A chemical sunscreen by the name of oxybenzophenone, which is this molecule here, absorbs in the UV range. Because it absorbs in the UV range and you put it on your skin, it protects your skin from the UV light. Now, a conjugated system, when you have three or more atoms that are sp2 hybridized, is a very stable system. And the reason for that is because we can delocalize all of these electrons. That's what makes an allylic carbocation very stable. Once we have lost the octet on carbon, then we have an sp2 hybridized carbon. That p orbital is empty. And because that p orbital is empty, it can delocalize these pi electrons. That's what makes allylic carbons so stable. Dienes, when we have two pi bonds in a system, and they're conjugated, they can adopt two different conformations because that single bond, that sigma bond, has free rotation. So because that sigma bond has free rotation, we can adopt what's called the S-cis, where when looking at the sigma bond, both of the pi bonds are in the cis position or the same position. Or we can have what's called S-trans. Again, with relation to the single bond, the pi bonds are on opposite sides. Now, because there is free rotation, the conformers, the energy barrier is very small. And this happens at room temperature all the time. Now, the trans conformer is often more stable than the cis, but the cis imparts some interesting reactivity that we'll get to. More than one pi bond in a molecule, we call it a diene when we have two. Like naming our alkenes or our alkanes, we have to find the longest continuous carbon chain that contains the functional group. So in this example, we would have a hexane if this was an alkane, but it's not. Not only do we have one pi bond, we have two. So we use the suffix diene. So this would be a hexadiene. Now we have to give those pi bonds an address. We have to say where they start. And they start at carbons 2 and 4. Then we go through and name our substituents. Give them an address as needed. So that's how this name comes about. Now we can also indicate the stereochemistry around these double bonds. And that would be a really good idea. For this example here, we have both 2 and 4 trans. So we would call this 2-bromo trans 2 trans 4 hexadiene. Just as we have here, this is carbon 2. This is a cis. See, our hydrogens are on the same side, so this is cis 2. And then this is carbon 4. and the hydrogens are on opposite sides. So this is cis-2 trans-4 octadiene. Now, when we have an isolated diene, we have just a simple 1,2 addition, and this is just like we would react as if we were just looking at our alkene. So as before, the mechanism, our pi bond acts as a nucleophile, comes after our electrophile, which in this case is a hydrogen. That adds the hydrogen in a Markovnikov fashion. So the hydrogen goes to the least substituted carbon, and then we form our carbocation. Then our bromine attacks that carbocation, and we form the expected product. Now, of course, take into account the stereochemistry. The bromine can be up or the bromine can be down, because we did form that carbocation. It can attack from either side. That's what we expect when we just have an alkene. So when we have one equivalent of our hydrogen and halogen, then we can expect the simple Markovnikov 1,2 addition of hydrogen to the least substituted carbon and bromine to the most substituted carbon. Now, when we have a conjugated system, however, and I'm going to move over to this slide, when we have our conjugated system, then we can also form what is called the 1,4 addition. And that's specific, that's indicative of a conjugated system. So although we're going to have our nucleophilic pi bond come in after our electrophile, we're going to have that Markovnikov addition, and we have that allylic carbocation now. I'm going to leave my nucleophile up here. We can have rearrangement. So this pi bond can come in and it can satisfy that positive charge. It can stabilize it. So we can form the other allylic carbocation. Because it is allylic, it is stable. Now it looks like a primary carbocation, but remember this is an allylic carbon. So now that chlorine can attach at the end. So not only do we have the expected 1,2 addition, and this is carbon 1, this is carbon 2, 1, 2, at least in this view. When we name it, of course, we have to renumber in order to decrease the numbering on our functional group. Not only do we have that 1,2 addition, but we also have the 1,4 addition. So that's how we get those products from a conjugated system. Now, if our electrophile is an elemental halogen, like bromine, and really you're going to see bromine and chlorine added in a system like this, you can expect not only the 1,2 addition, but also the 1,4. So this is going to be a way that we can create a dihalogenated alkene. So the bromine is going to add across the double bond, across the 1,2 double bond. That's what we expect to see. That would be expected in any alkene. But because we have this conjugated system, you also have to take into account that we can have that rearrangement. So that pi bond can come in and satiate that charge, form that other allylic carbocation in order for the bromine to add. And that's how we get the 1,4 addition. So watch when you have a conjugated system, watch for the alternate that you can, or the additional product that you can form. Now you do have to pay attention to this stereochemistry. So for example, if we're going to have this substance, not only can we set it up so that we have the 1,4 addition. So this would be my double bond that I'm not touching. I would have my bromine here. Now my bromine, because this is a carbocation intermediate, can attach in both the forward and pushed back position, so coming out towards me or receding behind. but I can also form that 1,4 product. So I would have the rearrangement. Now just to go through this, I'm going to start at my carbocation here. To rearrange, the pi bond is going to drop over 1. Then I will form the new carbocation, which would be out here. This is the carbon 4. So if I'm numbering, now I'm looking to add my bromine here. Bromine, forgot to draw my bromine in. We'll add here in order to form the 1,4 product. Now again though, we can bring bromine from the front, or we can bring bromine from the rear. Now we can also form the cis products, but because it is more stable to form the trans products, our major products will be in trans form. Now we can control the products of our reaction by controlling the temperature of our reaction. We have both kinetic products and we have thermodynamic products. Our kinetic products will occur regardless of temperature or time involved. They happen very quickly. Now we can selectively produce our kinetic products when we decrease the temperature of our reaction. So in a 1,2 addition is a kinetic product, and that happens at low temperatures. We can adjust to make it more of our product mixture. So a 1,4 addition, that is a thermodynamically controlled product, and we will produce more of that when we increase the temperature. That when I say increase the temperature, it's usually more than about 40 degrees Celsius. About 40 degrees Celsius, we're looking at more than 100 degrees Fahrenheit. So this is pretty warm. Now this kinetic product is usually seen in irreversible reactions, where the thermodynamic product is usually seen when we have reversible conditions. So we can determine, or we can push which product we want to form by controlling the reaction conditions. Now the most important reaction we're going to talk about in this module is called the Diels-Alder reaction. The Diels-Alder reaction is a cycloaddition reaction. So we're going to take 2 reactants and we're going to make them a 6-membered ring. And we do that based on all of these pi bonds. We have what is called a diene, which we've been talking about. So that's a compound, and it's specifically a conjugated diene. And then we have what is called a dienophile. Usually a dienophile is going to be something that has some pi character to it. This is a concerted reaction. It all happens at once. And your diene has to be in this S-cis configuration. You see how the dienes, or both of the pi bonds, are pointing out towards our dienophile. Now this other pi bond sees a pi bond it likes, because it is a dienophile, and it will make a new bond. So this bond, this was our, I'm going to write it in red, CH2, this was our dienophile, and this was our diene. So you see we've created all these new bonds in order to form a new cyclic compound. Now this is enormously useful when we're talking about synthetic chemistry. So we have our diene, and again, we need to be in this S-cis configuration. So if something is locked in that S-cis configuration, it will react much faster. The dienophile is going to control the stereochemistry of the product. And a cis dienophile, you see the R groups on one side, that means hydrogens are on the same side, that's cis. That's going to create a ring with cis stereochemistry. A trans dienophile, here's trans, the H's are on opposite sides, as are the R groups, will create a trans ring. And you see this happens by creating 2 new sigma bonds. Well, I can't have that just attacking nothing, so we come out here. 2 new sigma bonds, and one new pi bond, but we're breaking 2 pi bonds as well. So we have this big flip-flop of electrons in order to create this new 6-membered ring. Now, when you have this S trans, remember the energy barrier is very strong, or it's very small. So this can happen, this rotation can happen at room temperature very easily. But it must be able to adopt that S-cis conformation. If you have 2 phenyl groups here, a phenyl group, and we'll talk about that soon, but a phenyl group is a benzene ring that's ready to react with something. It's got this either a plus or a minus or something. It's lost a hydrogen, but it's very bulky. If you have 2 phenyl groups, you're not going to be able to form that S-cis because the phenyl groups are going to be in one another's way. You have too much steric hindrance, you're not going to be able to form a Diels-Alder reaction. So essentially, the characteristics of the Diels-Alder cycloaddition reaction can be summarized with these 6 items. So the reaction will always create a new 6-membered ring. It can happen intramolecularly, so within the same molecule, but it will always form a new ring. The diene must be able to assume that S-cis conformation. If it is locked in an S-cis conformation, then it will react faster. So something that is locked in an S-cis conformation would be something like this 5-membered diene here. So we would have our dienophile that would attack from underneath and push this up. So we end up making a bicyclic, and I'll show you that in a moment. The computer generated is much easier to see than mine. So I'll show you that in a minute. But this is an example of something that is locked in that S-cis conformation. Now, electron withdrawing groups on the dienophile will make that reaction happen faster. What's an electron withdrawing group? Something that has electronegativity to it. It pulls the electrons away from that dienophile. An electron donating group on the diene will facilitate a reaction. So the more things it has inside or bonded, the more electrons are available to stabilize that whole structure. Steric hindrance at the bonding sites may inhibit or prevent reaction. As shown previously, the phenol groups would prevent that cis structure from forming because they would just interact. You can't turn that around. And the reaction is stereospecific with respect to substituent configuration on both the dienophile and the diene. Now, this is a case where working with your molecular model kit may help you, or if you can spatially recognize where these things are, that would also be a tremendous help. So here is that locked S-cis diene that I mentioned before. So here we have this cyclopentadiene, and it is locked in this cis structure. So what's going to happen is this dienophile is going to come in, react there and here, and then we push this part. Let's see if I can highlight it in a different color. So we push this part up, and we create this bicyclic structure. So you see there is a 6-membered ring on the bottom here. I'm going to count from the double bond. We are always making a 6-membered ring with a Diels-Alder reaction. But then we have this additional peak. When we have a bicyclic structure, so we have formed 2 rings in the same molecule, we have a new way to describe our substituents. And that way is by using what is called endo and exo. So you have to look at this bicyclic structure as inside the concave side and outside the concave side. So Here, our ring structure kind of forms this arch. So inside that arch would be called endo, and outside the arch would be called exo. Now, the endo position will be favored for substituents that when we form these bicyclic structures. Now, alkynes can also serve as dienophiles. Up until now, we've seen examples with alkenes as dienophiles, but alkynes can be dienophiles as well. Only one pi bond is going to react, however. So if you have a bicyclic structure that ends up with 2 pi bonds, that means your dienophile had a triple bond, because only one of those pi bonds will be used to make that new sigma bond that initiates the flip-flop of the electrons. Now, this is also called a pericyclic reaction or pericyclic reaction. It is a concerted rearrangement. It happens all at once, and it goes through cyclic transition states. Now, we have 2 intramolecular pericyclic reactions. One is known as the Cope rearrangement, where you can open, if you don't quite have a completed circle, you can form a new open side by rearranging intramolecularly. It could also be seen as if you have what looks like an open ring and you have a heteroatom, like it's an ether molecule but it's a diene, you can have what's called the Claisen rearrangement. Now, Claisen is when oxygen is involved, but Cope is when it is just a hydrocarbon. Both of these rearrangements require having our 2 double bonds with 3 single bonds between them. So that is what you need to look for before you can decide if there will be a rearrangement. You need double bonds with 3 single bonds between them. So let's look at these reactions. What would be our product with our Diels-Alder reaction? Because that's what we really need to practice with this particular module. Here, we're going to have this form a new bond here. We're going to drop a pi bond here, and we're going to form a new bond here. So that means I need to figure out where the methyl and my aldehyde group are going to go. Because I'm trans here, when I make my new ring, my pi bond is going to be here. So this is now my carbon 1, 2, 3. This is going to be 4, 5, and 6. So here's 6, 1, 2, 3, 4, 5. Because my dienophile is trans, then I'm going to put my methyl behind, and I'm going to bring my aldehyde group up on top of the ring. Here I have my dienophile, and it's going to come after my diene. And this is going to be tricky to draw. This double bond is not going to be reacted. So I'm going to have my 6-membered ring on the bottom. Let's see if I can draw it this way. Then I'm going to have my peak, this peak, and then I need to have the remainder of my dienophile. Here for C, I have a triple bond, so I know I'm going to end with a double bond. Now I am locked in this cis position, so here I'm going to come after this carbon, drop the pi bond, make my new sigma bond. So to draw this reaction, or to draw this product, I should say, 1, 2, 3, 4, 5, 6. So this, let's see if I can highlight it. This part here is going to be this part here. It is popped up. Ooh, wrong color. So now I have this to contend with here. So this part is going to come off this carbon. Now here, I have a diene and I have my dienophile, but this is locked in a trans position, so there will be no reaction between these two compounds. And for E, I'm going to come after this carbon, which is going to drop my pi electrons between these carbons. This one's going to come out to there. So my product then is a new 6-membered ring. But now I have to pay attention to the stereochemistry. So it's going to be, well, I have 2 cyanides here, so the stereochemistry really doesn't matter. One's in front, one's behind. And I'm going to push both of these CH3s up because this is a syn addition. It has to happen on the same side. You could just as easily have pushed both of these to the rear. So for F, here we have our S-cis diene and we have our dienophile. This is going to be tricky to draw. So my dienophile, I'm going to go this way. Pi bond drops. New sigma is made. So here's my new 6-membered ring with my methyls. I'm just going to leave them like that. New 6-membered ring here. So these carbons are these carbons. So I need to draw the rest of the molecule as if it is unaffected. So we've made this as our new product. Here, our diene in blue, our dienophile in red. I'm going to come after my carbon. We have our S-cis configuration here. Now I make my new 6-membered ring, but this time we are bicyclic. So I have my peak, my new pi bond. Let's see, that didn't quite work out. Now again, just to reiterate, this peak is this here. And then I draw the rest of my dienophile as if it is unreacted. So these carbons are these carbons. So I have an O there, there's an oxygen here, and I have an O here. Now for H, again, we have our diene. It is locked in an S-cis configuration, so it's susceptible. So I'm going to come after this carbon, drop a new pi bond, come after that carbon. Again, we're in a cis conformation for our dienophile as well. That means the stereochemistry of this is going to look something like, let's see, I'm going to take... So this carbon is that carbon. And my cyanides are both going to come out at me. You could just as easily have pushed them to the rear. It does have to be a syn addition, same side addition, and because my dienophile is in the cis position, that means my product must also be in the cis position. Now we have 3 reactions that we talked about in this video. So we have our isolated diene, and our isolated diene is going to react in a Markovnikov fashion. This isn't new. So if we have one equivalent of our electrophilic halogen here, then we can expect to make the 1,2 addition, and it is Markovnikov. H goes to the least substituted carbon, bromine to the most substituted carbon. Then we started reacting with conjugated dienes. Now when you have a conjugated diene in the same situation, then not only are you going to form that 1,2 addition. And here I'm just using one equivalent, so I'm only going to react one of those alkenes. So if I have my conjugated diene, then I can expect to form the 1,2 product as well as the 1,4, 1, 2, 3, 4, 1,4 product. Also, when you have a conjugated diene with a dienophile, so we have conjugated diene plus dienophile. Then we have what's called the Diels-Alder reaction. And the Diels-Alder reaction will always result in a new 6-membered ring. Now this is a 1,4 addition. So if we have our conjugated diene, 1, 2, 3, 4, I'm adding to 1 and 4. And then I'm just going to take my dienophile here, and then I form the addition product. So there are 3 reactions with this video.